Almost every commercial building and industrial facility relies on the automation of their mechanical and electrical systems. This trend is only set to increase, especially as larger, smarter, more complex systems and buildings are constantly under construction. So, how do we control these systems and what devices are used to achieve that? That's what we'll be. PLC stands for Programmable Logic Controller. There are many variations, but they typically look something like this. A programmable logic controller is basically a small computer that can carry out pre-programmed outputs based on inputs and a set of specific rules. They are used in commercial and industrial applications to control systems with minimal and sometimes even zero manual intervention. The operation can be a simple on-off control based on the status of the input, or a more sophisticated response based on calculations, sequence, and logic. Before PLCs, control was carried out via banks of relays. Each relay controlled dedicated inputs and outputs based on physical wiring. Relays would control other relays to form logic controllers. For example, with a simple AND gate, only when two inputs are energized, this one and this one, does the relay output energize. These inputs could be sensors, or they could be outputs from other relays. To change the operation, the physical wiring had to be changed. So the physical connections had to be altered if a different response was ever required. These old banks of relays were vast in size and very complex. This is an example of an elevator relay bank. And this is the relay bank from an old electrical substation. As you can imagine, these are not going to be easy to change, and finding faults can be difficult and very time-consuming. With the invention of solid-state electronics and microchips, the command logic part of the banks of relays could be replaced with software logic, and so PLCs quickly took over. PLCs vary widely on their application, but they all monitor their inputs, then make a decision based on a stored set of rules, and from those, they then output commands to automate a process. We often find relays used in combination with PLCs. The relays can directly deal with the automation tasks and communicate with the PLC. This will reduce the amount of programming required on the PLC and also free up storage space. PLCs are widely used. For example, when you check a bag in at the airport, the bag is given a barcode and it enters the conveyor belt. A PLC scans the barcode and, based on a set of rules, decides if the bag is diverted to either the domestic or international route. The next PLC scans the barcode and decides which city the bag needs to be diverted to. The next PLC decides which gate it also needs to be diverted to. And if all of this goes to plan, then the bag will arrive at the correct gate. First, we have the input modules or field sensors. These are the physical connections between the outside world and the PLC. These can be digital inputs, such as simple on-off switches, bimetallic temperature strips, presence or motion sensors, or even a float switch. These digital inputs can only provide information on whether something is either on or off, and nothing in between. For that, we would need an analog input. For example, a simple control knob, which ranges from 0 to 100%. This will go through a voltage transformer to give 0 volts at 0% and 10 volts at 100%. The PLC can scale the input to match the sensitivity required for very accurate output control. It could also convert the voltage into current using resistors and Ohm's law. The amount of current, usually measured in milliamps, tells the PLC whether something is performing between on and off. These inputs could be, for example, a thermocouple or a resistance temperature detector. It could be a pressure sensor or perhaps a strain gauge. These voltages or currents are converted into a digital equivalent number that can be understood by the CPU. We will look at that a little later in this video. Input modules will perform 4 main tasks. They sense when a signal is received, they convert the signal voltage into the correct signal for the CPU, they isolate the PLC from fluctuations in the input voltage or current signal, and they send the corrected signal to the CPU. The CPU, or Central Processing Unit, is the brains of the operation. It holds the program or software that decides what outputs are required by applying rules to the input signals. The CPU typically consists of a microprocessor, which does the work based on the input value and the logic in the program, a memory chip to store the program. This will also store the output history, any faults or alarms such as Modbus and LAN connections, which allow us to remotely communicate with, reprogram, or even monitor the device. Then there's the output modules, or field output devices. This is providing the signal to the device we are controlling. For example, a simple indicator light, a solenoid valve, a motor starter, a variable frequency drive, etc. There are some other parts, such as a battery to keep the PLC alive in the event of a power failure. There might be a small screen for a user interface to allow some configuration. There will need to be a time clock and calendar to operate a device at the correct time. And there will also need to be a power supply to provide the low voltage used by the CPU as well as the input and output modules.